All right, class, so this is an ALEKS topic that's called solving for a reactant using a chemical equation. And I really like this problem. It's got a lot of different aspects, a lot of the stuff that we've been talking about. I think it encapsulates a lot of the concepts. So let's go ahead and get started. The first thing in this problem is we're going to have to come up with a balanced chemical equation. So we're given these words. This is a major component of gasoline is octane, C8H18. So I might just go ahead and start by writing out C8H18. When octane is burned in air, so that's going to be with oxygen, it chemically reacts with oxygen gas, so plus O2, to produce carbon dioxide and water. So the first thing that I would write out on my piece of paper, right, is this chemical reaction. Now, at this point, this chemical reaction is not balanced. So we need to then balance the chemical reaction. So the first step of this problem, right, is coming up with what these words are telling us is our chemical reaction, and then the second step is going to be to balance the chemical reaction. So in order to balance this, if I'm looking at this, I'm going to start with a carbon. I got C8 on this side, so I've got 8 carbons on this side. I'm going to need 8 carbons on this side. That's the first thing that I'm going to do. The next thing would be hydrogen. I've got 18 hydrogens on this side, so I'm going to need 18 hydrogens on the other side, so I'll put a 9 there. Now we get to oxygen, and there's a variety of different strategies and methods. I'll talk about both of them real quick. The first thing that I would do is I would say, well, how many total oxygens do I have on this side? I can see that I've got 16 here, 8 and O2, so that's 16, and then 9 extras. So 16 plus 9, that's 25. So right now I've got 25 oxygens on the right-hand side, and I'm going to need 25 oxygens on the left-hand side. So one method is just to say, well, put in a fraction for what you will need in order to get 25 oxygens on the left-hand side. So the easiest way to do that is just put 25 over 2. That's the number I need, and I know that since I've got O2, it's going to be 25 over 2. What's not good about this is that we don't want to have fractions in our balanced chemical equations. So what I can do is I can multiply everything by 2. So that will end up being 2 C8H18 plus 25 O2 goes to 16 CO2 plus 18 H2O. And that is our balanced chemical equation. So now if we go through, we should see that we've got 16 carbons, 36 hydrogens, 50 oxygens, and 50 oxygens total. So this would be 32 plus 18 is 50 oxygens. So this is big numbers, right? But if we use our strategy, we go through one thing at a time, we should end up being okay with balancing this chemical equation. The other method is when you get to this fact that you've got 25 oxygens at this stage, and you know that you need to have an even number, then you can just go ahead and directly double everything. So just go ahead and double this 1, double this 8, double this 18, or double this to 218, and then figure out how many oxygens you're going to need. In that case, if you're going to double everything, you're going to need 50 oxygens, so that will be the 25 O2. Either method should get you to the same final answer. Okay, now we need to do the actual problem. So the question is asking us what mass of water, that's the question. So over here I might put mass equals question mark, is produced by the reaction of 8.24 grams of oxygen gas. So I'm going to start with 8.24 grams of O2. And I like to organize my work and organize the question in this way. So 8.24 grams of O2. In this case, we're going to assume that there's essentially plenty of gasoline, plenty of octane. This O2 would be what we consider to be our limiting reactant. And let's go ahead and do the problem. So I can see that this is going to be a stoichiometry type problem. I'm going to need to convert grams of O2 into moles of O2, and then moles of O2 into moles of H2O. If I want to find the mass of this H2O, well, I know that the ratio between oxygen and H2O is 25 to 18. But before I can use that ratio, I need to be in terms of moles. So going over here, I'm going to convert 8.24 grams of O2 into moles of O2. The way that I would do that is by using the molar mass of oxygen, so 8.24 grams O2 times 1 mole. Since it's O2, this should be 32.00 grams, and that's going to give me a value of 0.2575 moles of O2. Now, this number of moles of O2, that's going to be sort of the count of oxygen, right? And since the count of oxygen, then I'm going to be able to use that mole-to-mole ratio to figure out how many moles of water I'm going to make. So the whole point of the balanced chemical reaction, it tells you that 25 moles of oxygen is going to react with this 2 moles of C8H18 to form 18 moles of water. Whenever we're using these coefficients, we need to be talking in terms of moles. So the next step would be to use the mole-to-mole ratio. And that's going to look like this, 0.2575 moles of O2 times 18 moles of water. I'm using this ratio of 18 to 25 sort of as a conversion factor. So I'm going to convert from moles of O2, right, those units will cancel, into moles of water. And that ends up giving me 0.1854 moles of H2O. This is the amount of water that would be produced. So make sure you guys can see that. This is going to be the amount of water that would be produced if I did this reaction, right? If I was able to react this 8.24 grams of oxygen to form water, right, to burn in this gasoline, this is the number of moles of water that I would end up with. But we're looking for the mass of water. So the last step is really just going to be to convert. Let's put a little thing there. Make that look nice. Convert moles of H2O into grams of H2O. And I'm going to use the molar mass of water again, which is going to be 18.02 grams per 1 mole. My units of moles will cancel, and I end up with a value of 3.34 grams of water. It says round our answer to 3 sig figs, so I've already done that. 3 sig figs here, 3.34 grams of water, and that's it. So definitely a very common type of stoichiometry problem. Coming up with the balanced chemical equation, that's really the most important thing to do first. Once we have that balanced chemical equation, the rest of this is really basic stoichiometry, saying that this is my limiting reactant, this is what's going to run out first. Given that information, how many moles do I have? And then using the mole-to-mole ratio. This is stuff that we're going to be doing again and again and again. And you really need to sort of nail this down. So 3.34, that is my answer for this problem. Hopefully that helps.